All right, good morning. Welcome to week 5 Thursday. It's going so fast. Morning. Where all my peeps at? Well, they'll come trickling in. They always do. But we're rolling. Why? Because we got stuff. Because what, Tariq? Because what? Because summer. All right. What do we know? We know quite a bit about the respiratory system at this point. We know quite a bit. We know that, one, there's a lot to do with ventilation. We know this. We know this. It's an instinct now. We know that ventilation has to do with creating pressure gradients to be able to push air past these resisting tubes. Sweet. So airflow is proportional to delta P over resistance. We know a lot more about what's creating the delta P, and we know a lot more about what creates the resistance. It's not just the diameter of the tube anymore. We definitely still want to think about the elasticity of the lungs. We definitely want to think about surfactant and alveolar collapse and all that sort of stuff. But again, in normal physiology, an everyday healthy person, do we need to worry about surfactant? No. Do we need to worry about the elasticity of their lungs? No, they're healthy. That's something you want to make sure that you understand exists, because you're not always going to be dealing with healthy people. Cool. Now, once we can get air into the lungs, now we're going to have gas exchange. We're going to have gas exchange between the alveoli, and the blood. This is alveolar respiration, and this primarily depends on Fick's law. And as we change the variables involved in Fick's law, we're going to change alveolar respiration. Let's think about this in terms of something that we learned yesterday, which is that atmospheric pressure of oxygen, that partial pressure of oxygen, is approximately what? Just to keep going on this. Good. It's approximately 160 millimeters of mercury. And what was the partial pressure of oxygen in your blood? Yeah, 159.6. You're not wrong. That's why we just say 160. We're not worrying about the rest. What was the partial pressure of oxygen in the blood? It doesn't matter whether you're talking about the low end or the high end. Just give me a number, one of the two numbers. Not 150, much lower than that, much lower than that. Yeah, 104 at maximum. And what about the approximate minimum? Yeah, Andy, you're not wrong. 100 is kind of where I get to there. No. So 100 is like saturated. Okay, that means that basically all of the blood is taken care of. But what about the arterial return to the pulmonary circuit? It's already poorly oxygenated. How many millimeters of mercury are left then? Yeah, good try, Heather. Good. Yeah, and don't forget the less than sign. I know it seems trivial. Good, Ash, but that less than sign is really important because it all depends on metabolic demand and oxygen usage. Does that make sense? Yeah, Heather, yes, 45 is CO2. Good. So let's think about that. Whether it's 160 to 100 or whether it's 160 to 40, either way, air, oxygen should be diffusing from this number, because it's bigger, towards that smaller number. So let's go ahead and use the 100, okay, because 100 millimeters of mercury is about saturated. This is going to be in that venous return, the pulmonary veins. So pull V partial pressure of oxygen is about 100 millimeters of mercury. It's saturated. But what I want you guys to think about using Fick's law is just changing the amount of atmospheric oxygen, just a little bit. Whether it's because the weather gets too hot and too humid, and this number drops to 155, or whether you are climbing Mount Everest whether you get off a plane in Colorado. Colorado's kind of funny that way. If you go into the Rockies, the mountains are really high, but you guys know how they call Denver the Mile High, of course, right? Mile High City. Salt Lake City is actually higher. And that's why, you know, Olympic athletes, they're going to train in Salt Lake City, outside of Salt Lake City, and not typically outside of Colorado, because Salt Lake City area is actually a lot higher, so their body trains better. Sorry, I had to type something real quick. Now, you guys understand that as somebody goes up in elevation, the air gets thinner. If you heard this, if you haven't, maybe now's a good time to learn about it. The air gets quote unquote thinner, and what that means is there's less and less oxygen per volume of air. So you're losing oxygen, the molecules of oxygen. There's less of them up there. So what starts happening to the partial pressure of oxygen as you go up in elevation? Increase, decrease, no change. So what's going to happen to the rate of diffusion of oxygen into the body if this number here drops to 140 millimeters of mercury, for instance, or 120? What's going to happen to that rate of diffusion? Increase, decrease, no change. Got just a couple people that are following along in chat. Increase, decrease, no change. I don't know whether I'm lagging. I don't know what's going on here, but yeah, I mean, clearly it's decreased. This is important. So I'd love for you all to work with me on this. Yeah. So 140 millimeters of mercury, and so what's going to happen to the overall amount of partial pressure of oxygen in my blood if I start to decrease this concentration gradient? Am I going to get a bloodstream that's 100% saturated? What's going to end up happening is that I'm going to be moving from 40, less than 40 millimeters of mercury. I'm going to be moving that blood past a smaller gradient. So 140 is trying to push its way into the bloodstream. Well, that's just not enough partial pressure to get the less than 40 up to 100. So instead of going to 100, this value is going to end up being lower. And let's say, for instance, it's 90 millimeters of mercury instead, right? So this is at elevation. We'll do an @ sign. So now this is going to be the venous return to the heart. The partial pressure of the venous return to the heart is going to be 90 millimeters of mercury. What's your body going to be saying? Sweet, lovely, wonderful, woohoo! Yeah. So we're going to have what's called a hypoxia. Hypoxia is technically any time hypoxia is defined as being a situation where your blood is less than 60 millimeters of mercury. And hypoxia occurs pretty rapidly at elevation, okay, where your blood is at 60 millimeters of mercury, not at 100 millimeters of mercury. Pretty big difference, right? This is going to come back and play a role in lots of other things. But what do we already know about hypoxia from earlier this semester is that let's not forget to tie in the rest of our semester. Our body is monitoring for hypoxia all the time. It's our kidneys that monitor for hypoxia, good old kidneys. They're monitoring the blood for hypoxia. And what did the kidneys release? Does anybody remember from Unit 1? What did the kidneys release during a hypoxic event? This is when I was talking about Lance Armstrong, if that helps you ring a bell. Yeah, a hormone, for sure. For sure. Which hormone is going to be released during hypoxia? Erythropoietin, EPO. Good, Parker. Does that ring a bell for everybody? Why is that important? Because when erythropoietin gets secreted, what's going to end up happening to the number of red blood cells being produced in the body? So we're going to be increasing erythropoiesis, and that's going to increase the number of RBCs. So what's going to happen to the oxygen carrying capacity of your bloodstream? Increase, decrease, no change. And so now we have more erythrocytes to be able to carry oxygen. The more the erythrocytes there are, these lower atmospheric partial pressures of oxygen, we're now going to have more erythrocytes to pick up the smaller amount of oxygen that's around. And that's going to allow your blood to get back to the 100 millimeters of mercury saturation, because there's more erythrocytes available to pick up less oxygen. It's pretty cool. This is why athletes train at elevation. Because if you train at elevation, you put your body into hypoxia, you force your body to produce erythropoietin and to make more RBCs. And you train and you train and you train, and then you go and race at sea level, and you're a beast. Okay? You're in essence, you're doping, but you're doing it legally with training. What are some other people? What are some other people? What are some other things that athletes do? Okay, another thing that athletes like to do is they like to train. If they can't go up in elevation, they train with masks on, exactly. And those masks that they're training with, those are O2 deprivation. Yeah, you're not wrong, Tariq. And some people do anything to get ahead. But the mask that they train with, that's going to limit the amount of oxygen that their body gets as they're training. So, exact same idea. If we force ourselves into a hypoxia as we're training, your kidneys are going to make more erythropoietin. Therefore, you will have more RBCs and you'll have a better O2 carrying capacity. So when you go to do your sport, football, whatever, boom. Trust me, I've thought about this 1,500 times, and you're not wrong. If you're not wearing your mask all the time, then you go to put your mask on and then you start rebreathing your CO2 a little bit, especially if you don't have a good mask. There's definitely times where people are going to be feeling lightheaded because they are hypoxic, but they're not wearing their mask all the time, so they're not going to get as much EPO. They're not going to get as much training in that. All right. This is not down a rabbit hole, by the way. This is definitely something that I can test you guys on. I love testing you guys on things that link to previous units. I love doing it. You can never forget about those previous units. Any times that they overlap, you guys better pay attention, okay? Because physiology is cumulative. Everything we do. Now, Heather asked one other question yesterday, and you guys been hearing about these oxygen bars? The oxygen bars are all about Fick's law too. Because now if we do something that is medical grade oxygen, now we're forcing in something that's like, you know, a massive load of oxygen. Basically air that's just hypersaturated with O2. So this number over here is like 500 millimeters of mercury or 300 millimeters. It just depends on the purity of the oxygen that you're going to be getting. So what just happened to the rate of diffusion at an O2 bar? If we raise this up to 400 millimeters of mercury, for instance, boom, we're hypersaturating our blood with oxygen. We are definitely going to have our bloodstream at 100% capacity. Does that make sense? And there are a lot of places around the world where the partial pressure of oxygen is pretty stagnant. The extra oxygen isn't, nothing could get done to it. It can't even get into the bloodstream, Heather. All that extra oxygen, it's hypersaturated. So, I mean, once you lose that concentration gradient, and once your red blood cells are saturated, which we'll talk more about today, but once all of the hemoglobin have oxygen bound to them, you can't bind more oxygen. That's just not possible. Hypersaturated about 104, 105. Yeah, exactly. You got it. That's maximum. With normal erythrocytes. If you start throwing in some more erythrocytes, you know, if you're an Olympic trainer or something like that, then you can get a little bit higher than 104. But that's what those O2 bars are, because, you know, there's a lot of places in this world where the partial pressure of oxygen in the air that you're breathing is just, it's not good. There's more molecules in the air. Smog molecules, not good molecules. Or, you know, high allergens and stuff like that, lots of dust particulate. Now all of a sudden oxygen's competing in the air with other molecules that normally aren't there. And so that's what those oxygen bars are so good for in places like Hong Kong, because the air's thick. All right, cool. I mean, that's what I'm saying. You know, as we go through each one of these, there's always something new to think about, which is the reality of physiology. 3, transportation. Now, transportation is going to have a lot to do with these saturation levels that I've been saying over and over and over. Because when we're dealing with transportation, I have not. No, I haven't done any of those oxygen things, but I'm definitely interested. Transportation. We need to think about both oxygen transportation and CO2. If you're already pretty fit, Heather, which I know you're, you know, a personal trainer and stuff, so you're already going to have pretty good oxygen. But yeah, I don't know what's going on there with those oxygen shots. Let's see, O2, we need to think about O2 transportation. And what did we learn yesterday? Is oxygen super soluble? It's funny, Tariq. Is oxygen super soluble? It's really small, but it's extremely non-polar, right? If it was polar, it would be dissolving in water. This is extremely non-polar, so very, very little of it can dissolve. Only 2% dissolves in that bloodstream. Whereas the rest of it, well, that's what our RBCs are all about, right? The red blood cells have hemoglobin. The hemoglobin has heme groups on it. 98% of this oxygen binds to heme. And this is a pretty big deal in terms of what you guys need to know for your test, because this has to do with saturation of your heme groups. Let's go to a graph. And this is also part of your lab reports and everything. Exchange and transport, what do we know about it? Fick's law comes into play. We definitely have a distance and a big, huge surface area, highly permeable oxygen, and we have concentration or partial pressure gradient. So yeah, all of that comes into play. We've talked about this a lot already. We have oxygen that's being transported by the red blood cell, and this is a hemoglobin molecule, and right in the middle of this cool little thing, that's a heme. That's a heme group. So when oxygen's bound, it's called oxyhemoglobin. And when oxygen's not bound, it's called deoxyhemoglobin. Easy peasy lemon squeezy there. We've already kind of covered that in Unit 1. But why is this important, and how can we use it clinically? That's what we're always trying to ask ourselves, is not just let's learn this because I have to learn this, but let's learn this because this is often used in differentials and diagnostics in clinically relevant situations. So what we have here is called an O2 hemoglobin dissociation curve, otherwise known as a saturation curve. So this is a oxygen saturation curve. Can you guys just write that term down in terms of something that you guys will need to know? Is you have to have a base understanding. I will not make you draw this, but you definitely need to know about O2 saturation curves. Got it. You guys got it written down in your notes somewhere, I'm sure, too, right? Make sure you highlight it, underline it. It's a good time for your tattoo. Now, what I want you guys to see, let's just look at the right. Let's not even look at the graph yet. Let's just look at the right. There's a great little table right here. Let's just look at these different partial pressures of oxygen. So if we're talking about the bloodstream and we're talking about the partial pressure of oxygen in millimeters of mercury, if the partial pressure is down at 10, that's pretty low, right? How much of your hemoglobin will be saturated? Well, it turns out that when the partial pressure of oxygen is this low, only a very small fraction of the hemoglobin in your body can even bind the oxygen. There's just not enough oxygen, right? So it turns out only about 14% of your hemoglobin will be saturated. Does that make sense? Just a straight number. Don't think about anything else. Now let's go not very far. Let's just go up to 40. At 40 millimeters of mercury, how much of your heme groups, how much of your hemoglobin is saturated? 75%. So what does this mean? Just real quick, what does this even mean, 75% is saturated? Well, let's not forget that all hemoglobin, okay, one hemoglobin molecule has 4 heme groups. Does that make sense? One hemoglobin molecule has 4 heme groups. So if I'm at 75%, that means all of my hemoglobin, in essence, have 3 of the 4 heme groups bound up. Yes, no? Cool. I think that's a helpful little, just stop, make sure you understand that concept, and then move on. Now let's keep going up. At 50 millimeters of mercury, we're at 85%. At 60, we're at 90. What do you guys notice is happening to the differences between these? So as we go up 10 millimeters of mercury, we get a huge change down here at the low values. But at these higher values, 50, 60, 70, 80, we're going from 85, 90, 93, 95, 90, 100, 105 over here. We're going 97, 98. Now we're stuck at 98, right? That change in the percent saturation is getting smaller and smaller and smaller. True story? Why is this? Because once you start saturating that blood, it starts to get harder and harder and harder to bind new oxygen to those hemoglobin groups. Once we start to get saturated, there's less and less sites available for that oxygen to bind to. So it's got to eke its way through the system and find what it needs to find. 1 second here. All right. Anyways, yeah. So what I want you guys to do next is I want you guys to tell me what is the partial pressure of oxygen in those pulmonary veins, leaving the right side of the heart, going out to the lungs. What's that partial pressure of oxygen? It's a nice connection to everything going on here. What's that partial pressure of oxygen? Pulmonary veins leaving the right side of the heart. We're leaving the right side of the heart. Okay, let's stop. Yeah, good job, Andy. Not a problem, Ashley. Not a problem, Tariq. Let's think about this. It's leaving the right side of the heart. Is it oxygen rich or poorly oxygenated? Right? It's poorly oxygenated. So am I going to be a high number or a low number? Relative low, right? Does that make sense? So let's do that again. What's that partial pressure of oxygen in blood returning to the lungs? Good. Did that help? Did that visual, it seemed to help, the people that are actually writing. Awesome. That's a great way to always take a step back. Always remind yourself of those basics. Less than or equal to. Yep. It's going to always be a little bit less than 40, but yeah, just depends on metabolic demand. So let's look at this saturation curve. And let's take this green line, and I'm going to move it over here. Because on the x-axis, the partial pressure of oxygen is 40. And on the y-axis, well, where it crosses, right, where this line goes up, it hits this S-shaped curve, I'm going to put another line. And then I'm going to look at the y-axis and see where it crosses. So what value is coming out over here? Partial pressure of oxygen is 40. What percent saturation are we at? 75%. And you can see that that matches with the table over here too, right? So it's not like I'm trying to trick you guys up. Just there you go. That's how it works. No, that's not considered hypoxia. See, that's the thing. Hypoxia is when the partial pressure of oxygen drops below 60. I guess, yes. I'm so sorry. Yes, that is considered hypoxia, but it all depends on where we're at. How about that, Heather? This will make more sense in just a minute. Let's deal with this. Sorry, there's some more steps before you'll understand this dissociation curve, okay? All right, so now what was the partial pressure of oxygen as that blood is returning to the left side of the heart? Just stop yourself real quick. Just again, Tariq, if it's returning to the left side of the heart, is it oxygen rich or poorly oxygenated? Right, so it's going to the left side of the heart, so it's going to be oxygen rich now. Yeah, awesome. So now we're looking at about 100 millimeters of mercury, 104 max kind of thing. Make sense? So now we do the same thing. We come over here, we line this up. This is at about 104, 102, something along those lines. And then we look at where it crosses over here. So what percent saturation are we kind of stuck at over here? 98% saturated. 98% saturated. That's pretty darn saturated though. It's almost 100%, not quite 100%. What's going on with the other 2%? What's going on with the other 2%? Oh, it's dissolved. Exactly. It's forced into the plasma at this point. Nice. Good connection. I love it. Good job. So you can think of this dissociation curve as normal physiology, where the right side of the curve is the partial pressure in the lungs and as it returns to the heart. And down here at 40 is what's going on out in the tissues. So now the less than 40 millimeters of mercury returns to the heart. But what do you now see is that the erythrocytes returning to the heart, yes, poorly oxygenated blood, sometimes written down as deoxygenated. Is it deoxygenated? No, it's not deoxygenated. It's poorly oxygenated. It's still 75% oxygen. I mean, it's still, yeah. All right, cool, awesome. I'm glad you guys are making that connection now. Now you can see why I'm kind of adamant about not calling it deoxygenated. Now what's going to start to happen as those cells use more and more oxygen, as the metabolic rate goes up, what's going to happen to the partial pressure of oxygen at the cellular level? Increase, decrease, no change. Should be a pretty easy idea. Okay, stop. The cellular level, because you can think about this both at the cellular level and at the blood level. So at the cellular level, if cells are using more oxygen, what's happening to the partial pressure of oxygen if it's using it? Increase, decrease, no change. Does that make sense, everybody? Yeah, cool. Yeah. So what's going to end up happening is more and more oxygen is going to leave the blood to go out to those tissues. So what's going to start happening to the partial pressure of oxygen in your bloodstream near tissues that have a high metabolic rate is that will also start to decrease, yeah? So at the cellular level now, if metabolic rate goes up and then metabolic rate goes up even further, look at what's starting to happen to the amount of oxygen left on our red blood cells. We went from 75% at 40 millimeters of mercury. We just dropped down to 20 millimeters of mercury, but how much oxygen is saturated now? We just lost 40% of our saturation. We only have 35% left. Pretty drastic, huh? Pretty drastic. Now, the last way that you guys are going to be using this curve clinically, I didn't see it as much until I became a parent. But every single time I started, I was taking my kid to, when he had horrible fevers, 104 and stuff like that, you take him to the, not the emergency, what's it called? Help me. My brain is blanking. Yeah, the clinic, urgent care, thank you. So you take them to urgent care, and what's one of the very first things they do? They check their temperature, of course, but then they put a pulse ox on them. You guys know pulse oximeters? I'll show you because I know not everybody does. So pulse oximeters, pulse oximeter. These are those little, you can either put it on, somebody's foot, or you typically end up putting it on their finger. You can buy these relatively cheap, and you can check your own pulse ox. My watch actually takes my pulse ox. It's a, it's a Garmin, so it's specifically for pretty hard exercise, and it monitors my oxygen saturation is how it works. So there are two laser beams, and basically as the lasers pass through your blood, depending on how much oxygen is bound to hemoglobin, the laser gets diffracted at different angles. And so the other side of the pulse ox now measures the diffraction of the laser based on how much oxygen is in your blood. It's absolutely insane. I love technology. It's so cool. They're kind of hard to use. You'll find that they're not always accurate. But a kid with a fever who's burning at 104, you guys are about ready to learn, that's going to have a pretty big effect on the partial pressures of oxygen, the saturation of your blood. What number should we want? What number do we want to see? What's the most ideal number that comes out of a pulse ox? Depends on whether you're looking at percent saturation or whether you're looking at the millimeters of mercury, whether it does the calculations for you, but most of these should be percent. 90, no. 95, no. What do we want that kid to be at, y'all? We're looking at the saturation of their blood. What do we want that kid to be at? Help me help you. Tariq, you got it already. We want them at 98%. We want them at 98%. So if anybody has had their kid at one of those urgent cares and it comes back at 90% saturated, well, let's go ahead and follow this along. It hits the curve right around there-ish. Let's drop it down. What just happened to the partial pressure of oxygen in that kid's bloodstream? And what did I say is the value for hypoxia? If a kid has 90% saturation, a lot of people can be like, hey, 90%, we're good. We still got 90% oxygen on our blood. What's the big deal? You guys start to see the big deal now? That's a big deal. That's a big deal. And during that peak, let's go to more relevant times now, which is whole COVID thing, right? During that peak COVID time when, these patients were going to the emergency rooms and hospitals, one of the key indicators for most hospitals to get a patient onto a ventilator, their percent saturation needs to be, somewhere around 80, a little bit, somewhere in here, 85 to 80. It just depends on the hospital and who's doing the managing of it. But let's go ahead and go to 80% saturated. So a patient comes in, they're at 80% saturation. What's the partial pressure of oxygen in their blood? Based on where my line crosses, yeah, less than 50 works for me. You guys can see that it's about 45 millimeters of mercury. How's that sound? That sure sounds like hypoxia to me, right? That sounds like the whole body is not getting enough. And that's why you get that patient on a ventilator. Yes, no, maybe so? Well, during the peak of the COVID crisis, there wasn't enough ventilators to get everybody that was dropping below 80. That's the thing. COVID affects your respiration. It affects how much oxygen can get into your body. And patients on the regular were coming in measuring less than 80% saturated. And it got to the point where if they were less than 80% saturated, right around 80%, I guess I should say, they were still sending them home. Yeah, exactly, Tariq. India is having a huge problem. There just wasn't enough oxygen available to put into these people. But yeah, let's say a patient comes in at 80%. You want to get them on O2 stat. You want to help them from having their lungs collapse. You want to get them pumping more oxygen into their body, because if we can now get more oxygen in, we're hopefully trying to get that partial pressure of oxygen up, therefore bringing that percent saturation of their blood up to some sort of level that is manageable. Crazy, huh? This dissociation curve, this oxygen saturation curve is a very, very powerful, very, very relevant curve for you guys to learn, especially in the world you guys are about ready to go out and work in. Okay? Why do we care so much about a patient that comes in, say, for instance, with 80% saturation? Well, we know that there is a disorder that's affecting this. Okay? What this disorder is doing actually is it's affecting the unloading of oxygen. If oxygen gets kicked off of that heme group, if oxygen gets kicked off of that heme group, then that erythrocyte is unloading faster. Does that make sense? So what sort of factors are going to affect the unloading of oxygen? How can we start to change this curve? Why would a patient come in and they're at, I don't know, 80% saturation? What sort of things could cause this? Well, that's what's over here on the left. We're going to go through this relatively fast, and I want you guys to, as you're studying, think about each one of these individually. First and foremost, well, it's all about the saturation of that blood based on how much oxygen is available. Easy peasy lemon squeezy. The more oxygen that's available, the more saturated the hemoglobin can be. There's more oxygen available to bind to hemoglobin. Doesn't get much easier to think about than that. If there's less oxygen, then less hemoglobin gets saturated. So we'll come back over here to the right side of the, and look at how this shift of the curve is going to occur in just a second. So next is the amount of carbon dioxide in the system. Carbon dioxide binds to the globin group. Yes, no, maybe so? And if that carbon dioxide binds to the globin group, then oxygen can't bind to the heme group. And so when the oxygen's released, the CO2, it basically comes in and crowds that area, and oxygen can't get back in there. So if the body has more CO2, it's going to be kicking oxygen off. Hydrogens. Hydrogens also bind to hemoglobin. They can't be on at the same time, Heather. They can't be on at the same time. CO2 displaces the oxygen binding site. Oh, very selfish. We're not even too selfish yet. We'll get down to selfish here in this slide down here. Hydrogen also binds to hemoglobin. And yet again, there's only basically one site for oxygen there. And if we start blocking that site for oxygen, it's going to start causing that oxygen not to bind. So the more hydrogen that's in the system, whatever that hydrogen's coming from, number one source of hydrogen in your body is one I was talking about yesterday, which is carbonic acid. We're going to get back to that in just a second. The more acid that's in the body, though, this could be lactic acid, this could be ketonic acids, this could be fatty acids, this could be amino acids. Any acid will end up binding to your hemoglobin group, and, well, it's an acid, so it starts to denature those proteins, and it kicks the oxygen off. Temperature. This is where fevers start coming into play. If we have a fever, the only cure is more cowbell. I already made that joke yesterday, but I had to make it again for those that actually know what the hell I'm talking about. But if you got a kid with a fever, remember, temperatures and molecules. Molecules move. all molecules are moving, whether it's in a solid state or a liquid state or a gas state, molecules move. And the temperature of the world around us changes how fast those molecules are moving. As you increase temperature, molecules end up with more entropy. They move faster. Pretty simple idea. And as these hemoglobins and oxygens and stuff are moving faster, it's going to end up kicking those proteins off. That's one thing. Now, if the temperature even gets higher than just, 101, we're talking severe fever, now we're actually cooking proteins. We're up at about 104, we're cooking proteins. If we make it to 105, 106, 107, danger. Yeah, exactly, Tariq. You were in the middle of writing that. That's exactly right. I was on my way there. You got it. Oh, hemoglobin can't function if it's cooked. No proteins can function if they're cooked. They're denatured. They get unfolded. That's part of the denaturation process. Proteins only work if they're folded. You cook a protein, it unfolds. It's part of the process. Last but not least, 2,3-BPG. You guys don't need to know what BPG stands for. It's also known as 2,3-DPG. All you need to know about this is that if you recall the anatomy of an erythrocyte, it does not have a nucleus, it does not have mitochondria. It is not using oxygen to make ATP. And it doesn't need a massive amount of ATP because it doesn't have a nucleus. However, it still needs ATP. Does that make sense to everybody? You got a living cell. It's gotta have energy. So red blood cells produce ATP through a chemical process that you don't need to know. And the byproduct of that chemical process is 2,3-BPG. So anytime the metabolic rate increases in erythrocytes, anytime those erythrocytes are making more ATP, they will produce more 2,3-BPG. And the way they get rid of 2,3-BPG is binding 2,3-BPG to, you got it, the heme group. It's got to bind to that hemoglobin, which displaces the oxygen and causes oxygen to unload faster. So the higher the metabolic rate in your erythrocyte, the faster oxygen will unload. Does that make sense? Yeah, we'll get there in just a second. You know I will. Well, I think you assume I will. So what sort of things might increase the metabolic rate of an erythrocyte? Well, let's first just start over here. T3, T4, y'all. What's the whole function of T3, T4? Increase metabolism. Yes, no? It increases the amount of ATP being produced in all the cells of your body. Epinephrine. What's the whole function of epinephrine? Boom, we need energy. We need fight or flight. We're running away from Mr. Axeman right now. Everything needs more energy. Growth hormone. Yeah, growth, energy. If we're growing, we got to make sure energy is available. Energy is available. Energy is available. All three of those should be relatively simple to think about. Yes, no? The last one's a little tricky just because of the wording, but increased arterial blood chronically undersaturated. What that means is if I have basically a hypoxic event, a constant hypoxic event, then the body is just struggling to figure out how it's going to get its ATP. Think of COVID. Okay, now I got a patient that's coming in and they are chronically undersaturated. They should be at 98% saturation, but say for instance they're at 85. Not life-threatening per se, but potentially very damaging. chronically undersaturated. Well, those erythrocytes are going to start to boost their production of ATP, making more 2,3-BPG. Make sense? This blue line is the new curve that gets drawn for these sorts of disorders, and it's called a shift, a curve shift. And this curve, the blue line, is it further to the right or is it further from the left of the S-shaped curve? This is silly, I know, but I just want you guys to figure out the wording on your own. Man, I got the road issues. So this is called a right shift. And if you're looking at an S-bend curve and you have a right shift of the curve, that is going to mean exactly what we've been describing, is that what's happening on the x-axis is going to have a huge impact on the left, the y-axis, but what it's going to do is it's going to make the y-axis stronger or weaker as you go up on the x-axis. That was a very confusing way that I just said all that. Listen, it's a right shift curve. So now if I was at 40 millimeters of mercury before in a normal healthy patient, what did we say that crosses the y-axis? At about 75%. But now I have a diseased patient. Where is it going to be crossing? Well, it's going to be crossing right around here-ish. So what just happened to the percent saturation? Increase, decrease, no change. So a right shift in that curve will always cause a decrease in the y-axis. Does that make sense? That's what I was trying to say, but my wording was really strange. So now if I come down here, if I have a right shift, which is the red line, then I have a decrease in where it hits the y-axis. But what if I have a left shift? Yes, that exists. If I have a left shift, what's going to happen to my saturation? It's going to increase, and that's a good thing, right? We want to, what? This is a good thing, right? This is not a good thing. And the reason, nice, Andy. Andy's just like, no, straight up, no. She's probably shaking her head. Why is this not a good thing? Because just because those erythrocytes are hypersaturated doesn't mean that they're releasing the oxygen. Perfect, Heather. Does that make sense, everybody? Rut-row. That's what these curves are dissociation curves. We need a perfect Goldilocks in between. If it's not Goldilocks, we got problems. So what's going to cause a left shift? The exact opposite of all this stuff, right? What if we have too little CO2? What if we have too little acid? What if the temperature drops? You see what I'm saying? All right, 54 after. Shoot. Okay. Quick. Most everybody in here has heard of carbon monoxide before? Well, tell me something in your house that's producing, or something that you use that's producing carbon monoxide. Car, absolutely. Love it. Wonderful. Somebody give me something else. By the way, carbon monoxide. Do you guys even know what? I never know where to stop sometimes. Do you know how carbon monoxide is even produced? It's just a CO group, right? Mono. Central heat. Yeah, so in terms of something that might produce it, absolutely. What's the number one way that our world is building up carbon monoxide? I love that you just said farts. I think that might be a first time. I think that might be a first time. You're not wrong, is that there's definitely some production of carbon monoxide out there um, by cows. But fossil fuels, y'all. I mean, again, it's fossil fuels that produces massive amounts of carbon monoxide. Anytime you have combustion, any combustion. So as you burn natural gases or oils and that sort of stuff, if you just burn wood, it doesn't have to be fossil fuels. Any combustion produces carbon monoxide. Okay, does that make sense? Just the number one source is fossil fuels. Now, let's talk about something that has combustion in your house. Central heating, yes, at a lower level. Yeah, your stove. Something else. Anybody? Keep going, keep going. Yeah, grills. Yeah, please don't use your grill in the house. Produces a lot of carbon monoxide. Actually, I shouldn't even make a joke out of it, right? A family died during the freeze because they brought their grill into the house to help warm their house. So, yeah, carbon monoxide poisoning is the real deal. Well, that's what we're trying to get to. Your oven, absolutely, to a small level. Fireplaces, if anybody has either, yeah, exactly, the chimney, right? If anybody has especially, well, it doesn't matter whether it's a wood burning or a gas burning, it's any combustion produces carbon monoxide. The tricky one that everybody always forgets, I swear, it's your dryer. Okay, your clothes dryer produces a lot of carbon monoxide. A lot. Just a recommendation. But you can't even rent a house, to a tenant without a CO sensor. Just a thought, right? There's families every single year, quite a few families every single year that go to sleep and never wake up because the dryers go wonky. And what happens is CO2 is emitted. And if CO2 is emitted in a high enough number, which happens again with, this is how some people commit suicide. They put themselves in a car in the garage, they close all the doors, and they turn the car on, and CO2 builds up, and they breathe the CO2. And CO2 is very, very powerful. It competes for that oxygen binding site. And I want you guys to look at this number, 240-fold greater affinity than oxygen for that heme group. This means that it binds to that heme group and never lets go. It takes a long time for carbon monoxide to fall off your erythrocytes, a very, very long time. So if CO levels get even remotely too high, that's going to greatly impact your saturation, your blood saturation. And so this is where CO2 poisoning comes into play, right? If there's I said CO2. This is where CO, carbon monoxide poisoning, comes into play. Because if there is carbon monoxide in the air, your erythrocytes will pick it up and it will block oxygen from binding. End of story. There's no displacement theory or nothing like that. This is just a massive greater affinity for that heme group. Okay, something to think about, but we need to get moving because it is already 10. Okay, now we already started talking about this slide yesterday. Carbon dioxide transport's even trickier than oxygen transport. Carbon dioxide, it's a little bit more polar than oxygen. 7% of it dissolves in that plasma. And that's about the maximum amount that can dissolve in your plasma. It's about the maximum amount that can actually dissolve in fluid at all. I'm not going to ask you guys a bunch of questions. I want you guys just to follow along here because time limitations, but think of a can of Coke. So what they've done with that can of Coke is they've actually forced carbon dioxide into that Coke. They force it. Now you got your carbonated beverage. You pop a top, your kids bug you, you forget it on a counter somewhere, and you come back about 6 hours later and you're like, I still want to drink that because that's like otherwise flushing money down the toilet. And then you go to take that drink, we got ourselves flat. Everybody knows flat beverages. So what's going on with a flat beverage is that only about 7% of a liquid can be saturated with or have dissolved carbon dioxide in it. Make sense? So a flat beverage is at approximately 7%. It's kind of like the maximum. Yes, no, maybe so? Otherwise, we're just forcing CO2 and closing off that system. But once you pop the top, CO2 starts to diffuse out. Awesome. Now, 23% is going to bind to the hemoglobin. Loverly. The other 70%, we went into quite a bit of detail, not enough detail. That's what we're going to do today. The other 70% is going to be transported as bicarbonate ion. It's not going to be CO2 at all anymore. It's completely getting converted to something different. The way this works is we're going to have a bloodstream. And in that bloodstream, we're going to have erythrocytes. Outside of that bloodstream, we have tissue cells, whatever they may be. Sideways columnar cells, whatever. Those don't really exist, but who cares? The RBC drops that oxygen off, and that oxygen is getting consumed. We make ATP. But we got some byproducts, CO2 and water. So what's happening to the CO2 concentration inside of these tissue cells? Increase, decrease, no change. So now we got an increase in the partial pressure of CO2 out here. It's at approximately greater than or equal to 45 millimeters of mercury. Whereas out here in the blood, it's at approximately 40 millimeters of mercury. You guys remember this? Therefore, CO2 will diffuse from an area of high to low. And CO2, nice simple diffusion, is going to come down, pass through, and it's going to enter the bloodstream. CO2 is always trying to go from an area of high to low. CO2 is always trying to go from an area high to low, always. So where's it going to go next? Well, let me walk you guys through this formula that we also talked about yesterday. Okay, if you just take CO2, let me use a different color. If you just take CO2 and start throwing it, we'll come back to that, Heather. It's not going to go to the lungs, not yet. It can't just get to the lungs. We're out in the tissues. We got to somehow convert it, bind it up, figure out how we're going to get it there. Okay, so CO2 now, we start throwing it at water. Chemical reaction. That's reversible. That's why we have an arrow going right and an arrow going left. This is reversible. Don't forget that. That's an important part of this process. This is going to make H2CO3, which was carbonic acid. Now, what I've alluded to yesterday a number of times, but didn't write it in because we just didn't, it wasn't relevant to the lecture yesterday, is that an enzyme, in the human body, chemical reactions are run by enzymes. Okay, this chemical reaction can occur at any time. Carbon dioxide plus water can occur anywhere. You know, it just in a glass of water in your kitchen. You can blow your breath down into that, and CO2 escapes your body, goes to that water, and it will produce some carbonic acid for sure, for sure, for sure. But if we throw an enzyme at this, enzymes are all about catalyzing reactions, making reactions occur faster. Your body has an enzyme called carbonic anhydrase. Anhydrase. Sorry for that little scribble down. You guys are going to be able to abbreviate that as CA. You can do capital C, capital A, or lowercase. I don't really care. Carbonic anhydrase. Everybody, what's the abbreviation for the enzyme that catalyzes the production of carbonic acid in the human body? Thanks for those that wrote in chat. Now, if on a test, hint, hint, or on a homework, hint, hint, I talk about the production of carbonic acid, hint, hint, and bicarbonate, hint, hint, if you write down that chemical formula and don't add in carbonic anhydrase, you will lose points. Is that clear? This is a critical part of this story. I hope I made myself clear. Now, here's the deal. Do we want to catalyze this reaction anywhere in the body? Do we want to just catalyze this reaction everywhere? Do we have this enzyme everywhere? No. We have enzymes in locations where we need that reaction to occur. Does that make sense? So, where do we have a high abundance of carbonic anhydrase? Anywhere we're going to be making lots of carbonic acid. So what sort of locations do we have for carbonic anhydrase? Number one, the one you guys definitely need to know for this portion of the unit, number one are RBCs, okay? Erythrocytes. Inside of erythrocytes, there is a very high amount of carbonic anhydrase that's being produced. So there's elevated carbonic anhydrase right here. Some other locations. CSF, cerebral spinal fluid. There's a lot of carbonic anhydrase in there. It'll make sense, just hopefully somehow. 3, another place we need to be thinking about carbonic acid in pretty great detail. All sorts of dang places, honestly. We're going to be talking about it in a lot of different details, but kidneys, we'll go straight there. We'll go kidneys. And there'll be a few other locations through the semester, but those will be some of the ones that you'll be tested on the most. So just to have that list somewhere so you're not surprised later. What does this all mean? If I have an area of the body, like the erythrocytes, CSF, and kidneys, certain cells inside those kidneys, that have a high level of carbonic anhydrase, what's going to be happening to the production of carbonic acid? Increase, decrease, no change. Good. And if I'm making more carbonic acid out of carbon dioxide and water, what's going to be happening to the carbon dioxide consumption inside of these tissues? Increase, decrease, no change. And therefore, what's going to be happening to the partial pressure of carbon dioxide inside of those tissues? Increase, decrease, no change. The partial pressure, because that carbon dioxide is getting used, the partial pressure of carbon dioxide inside that system will be relatively low. Yes, no, maybe so? If it's always being used, then that means it's not there. If I have more carbonic anhydrase inside of my RBC, that means that there's always going to be a relatively low partial pressure of CO2 inside of the RBC. Therefore, what's going to be happening to all this CO2? Well, immediately 7% of the CO2 dissolves. Sweet, awesome. Well, that's only 7%. So what happens to the rest is it's going to go into those erythrocytes. Because there is not as much CO2 in there, we got a concentration or a partial pressure gradient, and that CO2 goes into those cells. Make sense? I shouldn't have an arrow from the 7% dissolves. I'm going to go 93% enters RBCs. Now, of that 93% that enters the RBC, 23% is going to start to bind to hemoglobin right off the bat. It's getting attracted to the RBC because of that partial pressure gradient, and now 23 binds to hemoglobin, technically the globin group. The other 70%, sweet, we already got this process going. The other 70%, as we said, is going to be converted to bicarb, ultimately. So we want to write that in, and we're going to figure out how we get here. This is a big question mark. It's the hardest part about this whole thing. Well, maybe. It's definitely not trivial. The reason it's going to be converted to bicarb is because bicarb's easier to transport. Bicarb is readily water soluble. So if we can get this bicarb out into our blood, we can transport it in our blood in this form. How does this all happen? As the CO2 diffuses into the RBC, there's a high amount of carbonic anhydrase here. If there's a high amount of carbonic anhydrase, the CO2 that's diffusing into that RBC is going to react with water to make carbonic acid. An acid in water dissociates. All acids, when placed in water, will dissociate, which means the ionic bond is broken. What's that ionic bond? It's between a hydrogen group and a bicarb group. There is an ionic bond that's holding the carbonic acid together, and it immediately donates that proton, exactly, into solution. Well, now we're producing more hydrogens. And there's an issue that comes about from this that we're going to deal with later when we start talking about the kidneys and stuff like that. But most of these hydrogens, not all of them, but enough for the purpose of what you guys need to know for this unit, is that these hydrogens are going to go try to bind to hemoglobin. But now we got a bicarb issue. Why is this a bicarb issue? Because where was this bicarb produced? Is it being produced in the plasma, or is it being produced in the ICF? RBC, but plasma or ICF? Good. But where is it transported? What's transporting it? It's being transported via the plasma. So this is our problem, is we have to convert it to bicarb, but we have to transport it in the plasma. But this is an ion with a big, huge charge. Can that just make it through the cell membrane? Easy peasy lemon squeezy, right through that erythrocyte cell membrane? No, this thing is charged. It's polar, right? It's an ion. It's not technically polar, but you get my point. It's this huge charged ion. It cannot make it through this cell membrane unless it has help. Yes, no? Not an Uber. I like that you went to Uber there, but this isn't non-polar. So once it makes it out in the plasma, it can actually transport itself. This is, you know, this is very self-efficient automated driver. it's just gonna dissolve once it makes it out into the plasma. But we need to get it there first. So how do we get things anywhere? We need transporters. Okay, not carrier proteins, we need transport proteins. Those transport proteins are found in cell membranes. Yes, no, maybe so? So we need to take the bicarb that's being produced inside of this cell, and we need to somehow get it out of this cell. We need to. We got to figure out how we're going to do this. Well, the way this works in the human body, the primary method for moving bicarb around is by exchanging it with chloride. So this is a new transporter. You guys have never learned about it before, but this is going to be a very important transporter for the rest of the semester. So you must know this one, you must know this one, you must know this one. It's going to exchange it for chloride, and chloride levels are high out in your plasma, and it's going to use the energy of this particular transporter to be moving bicarb out into the plasma. This transporter has a very convoluted, its name is actually a bunch of numbers and letters. So what you're going to have to learn this as for the rest of the semester, and I want you guys to always remember this, if I'm moving bicarb around, I'm exchanging with chloride through something called a chloride shift. This is a chloride shift. So if I ever mention moving bicarb around in exchange for chloride, what I'm referring to is a chloride shift. So this bicarb that was just produced inside the cell is going to be transported out of that cell via chloride shift. Go ahead and everybody write it in chat. What transporter am I using to transport bicarb out of the cell right now? Chloride shift. Chloride shift. Why is it chloride shift? We'll get back to that. We'll get back. That's important. Okay, so now bicarb is in plasma. HCO3 in plasma. Sweet. That's where we needed it to be. Now we get all this bicarb that's dissolved in the plasma. It can act as a buffer as it's out there too. So it's sweet. It's this dual purpose. Huh. But we still breathe out CO2, right? How does that all work? Before we go back to the PowerPoint presentation, I want you to remind you guys about how chemical reactions work. I'm always, well, it is what it is. Students' backgrounds in chemistry is relatively minimal. Let's just put it that way. And it was not my favorite of subjects either. So here's a simple part about chemistry that is overlooked very often, is that chemical reactions are just like everything else in the universe. They want to go from an area of what this means is this chemical reaction that's right here is reversible, and it's all based on the concentrations of the molecules that are available. If there's more CO2 than there is carbonic acid, what direction is this equation going to go? What direction will this chemical reaction go? Will it go to the right or will it go to the left? there's more CO2, it's going to go from an area of high towards this area of low. Does that make sense to everybody? But what if there's more carbonic acid? What direction is this going to go? Remember, enzymes just catalyze reactions. They don't care what direction that reaction goes. So if I were to ever get into a situation where there's more carbonic acid in the system, this equation is going to go to the left. Does that make sense? And that's going to give us more CO2. Let's make this happen. I'll try to make this fast. I know I suck at making things go fast. I don't know why. I think it's the online, because summer. No, I think it's the online scenario here. It's just, I'm always having to still ask questions, but I have to wait for responses, and it slows everything down just a little bit. All right, so everybody just follow along. This part you maybe have already drawn in, but you can draw it again on your own. Right now, just follow it along. So put your pens down, please. Put your pens down. What do we know? We know that cells are producing more CO2 because they're using the oxygen to make ATP and the byproduct CO2. That CO2 is now going to diffuse from high to low, and as it enters the blood, 7% of it immediately dissolves. The other, whatever I wrote, 93% is going to enter the RBC because the concentration of CO2 in the RBC is relatively low. Okay, that CO2 is now going to be binding to hemoglobin. That's one thing that can happen to it. 23% of it's going to immediately bind to hemoglobin. But what happens to the rest? CO2 mixes with some water, shake and bake with some carbonic anhydrase. And what have we produced? We produced carbonic acid. However, we're inside of a cell, ICF. So there's lots of fluid. And that carbonic acid will immediately dissociate into a hydrogen ion, which goes to bind to hemoglobin, and a bicarb. The bicarb concentration inside that cell is increasing, and we need to get it out into the bloodstream. The transporter that we used for that is called chloride shift. How do you guys feel about this side? Don't worry about this yet. You guys feel like you can sit down and draw out that flow chart and think about each step? Nice, that's what we're after. I love it. Now, what's going to happen, and why is chloride shift called chloride shift? In the systemic circuit, the signals, there's local cytokines that the body's giving off all the time, these local chemical signals. The signals of the body tell the chloride shift to move bicarb out of the cell, but the difference between the pulmonary circulation and the systemic circulation, because all this blood's going to return to the lungs, well, in the pulmonary circulation, there is a cytokine, there's this local signal that tells the chloride shift to shift. It flips the transporter in the cell membrane. It literally flips it over. It shifts it. That's why this is called a chloride shift. And if I was transporting bicarb out of the cell, but now I flip that transporter, what direction's bicarb going to go? Back in. And what do we know about all chemical reactions is that they run on the gradients. Everything's trying to move from an area of high to low. So the more bicarb that's in the system, the more carbonic acid will be created. The more carbonic acid that will be created, now we're moving to the left on that equation. The carbonic anhydrase will start converting that carbonic acid to CO2 and water. Now CO2 concentrations or partial pressures are building up, and CO2 is very, very diffusible, right? So it's just going to diffuse, boom, boom, right out into those alveoli from an area of high to an area of extremely low, 0.25 millimeters of mercury out here, and we breathe out. Everybody good? It's a step. But I think the most important step here is there's two. one, understand that chloride shift shifts, and two, understand that chemical reactions run from high to low. That's why I make sure to mention that. I hope that's helpful in your understanding. There's another diagram that shows the exact same thing. I want to make sure you guys see it from different angles, but everything in here is exactly the same as it is here. So you only really need to study one of these. But this is systemic, this is pulmonary. The difference between these two areas is the chloride shift. Chloride shift up here is moving bicarb out. Therefore, the chemical reaction's always moving towards bicarb versus chloride shift in the pulmonary circuit. The chloride shift is moving bicarb in. Therefore, high, always moving this equation to the left. Yes, opposite. That's a nice, simple way to put it, Heather. They're always going to be opposite effects because of the chloride shift. Cool. All right, so here's what's going to have to happen. I'm not going to skip over nervous control of ventilation. I just refuse to do that. I will make time on Monday to do that. However, next week is digestive system, and digestive system is just as intense as everything else that we're going through. Mondays, oh shit, no, there's a holiday on Monday, so this gets even more complicated. I even sent out an email about that, right? Monday is a holiday, so we are even more complicated, aren't we? We got a scheduling issue, and that scheduling issue is that there's a lot to learn in a very little period of time. So what I need you guys to come prepared is that your homework, I'm so sorry that there's even homework over the holiday weekend, but your homework is to make sure that you're studying this digestive anatomy before coming to class on Tuesday. And there's just no if and or buts about it. You have to study this digestive anatomy before coming to class on Tuesday. I mean, you don't have to. I'm not grading you, but I think you'd be crazy not to, personally. Let me go in here. Where is my blackboard? Aha, aha. Let me remind you what you guys have available. All of the respiratory PowerPoints are narrated for you already. So even the one that's respiratory 4, which is all about nervous system control, you must know this for the exam. So I'm going to summarize it for you guys on Tuesday. I'm going to say, here are the important parts. I'm not going to talk about every little bit. So if you want to get those important little bits, then you need to go to this narrated PowerPoint. Digestive system. What I'll do for you guys tomorrow or today, one of the two, is I will figure out a way to make a recording for your digestive anatomy. Yeah, we could, absolutely. I just don't want to, you know, I don't want anybody that's not able to make it on Fridays to start feeling super left out. I'm not going to go through like lecture materials on a Friday. Does that make sense? Just for the mental health of all of the students and for me. But I can definitely make a narrated PowerPoint of the anatomy. It's just an anatomy overview. The good news about the anatomy of the digestive system is that we cover it again when we talk about the digestive 2 physiology and digestive 3. I know, I appreciate the heck out of that, Tariq. I'm kind of the same way as you, but let's just, there are students over there right now on the other side of the computer like, hell no, I don't want to lecture on a Friday. So, and I get it. I want to try to make this fair for everybody. Digestive 2, Digestive 3B. So the Digestive 2 and 3B, I'll make one specifically on anatomy. I've never done it. I've been meaning to do it, but I just haven't done it. One other thing to point out, I know if you need to go, you need to go, not a problem. You can get caught up with your lab groups and stuff, but I want to make sure you guys know what's available to you. Actually, it's in homeworks. It's in homeworks. If you go to the homework and reviews for this unit, you'll notice that the homework 3 is available. The review for 3 is also available. But I also created, this is the only unit I've done this for because it takes a lot of work, but I've also created practice exams for both the respiratory system and the digestive system. So you can just go in and begin that practice exam. And you can walk through, I put a lot of questions in here. I just kind of dumped tons of questions. So practice exam, 52 questions of practice. Practice? Okay, so you might as well get started. You know what I mean? Jelly beans? When blood passes through systemic capillaries, the oxygen saturation of hemoglobin changes. From what to what? Perfect. Why is there some image issues? What's going on there? Anyways, so great place to get studying. Great place to get studying. You guys want to, I'm sure you just want to. You're dying to start to study. That's just under homework and reviews. I try to put everything consistent. If you're studying for your exams, then it's in homework and reviews. Exams and practicals, that's where you just go to take your exams and practicals. But yeah, it should all, your screen won't look like my screen, so it should all be in nice order for you. Unit 3, Unit 3, Unit 3, Unit 3. Okie dokies. Keep up the great work. Study. Get your stuff done. Have a great 4th of July weekend. Enjoy your holiday, but don't forget about your work too. Bye-bye.